Welcome. Tonight we're going to work on interpreting the derivative as a rate of change. The last couple of days we've put a lot of energy into the mechanical work, just the grinding, paper and pencil process of finding a derivative, and now we're going to eventually put it to use and just get a glimpse of how it pertains to engineering and all sorts of real-world applications. And the second half of our video will be devoted to particle motion. It'll be a brief intro to particle motion, and as BC students, this is going to play a major role at the end of the year when we get into parametric functions. Okay, first things first, we want to just clarify some notation, and we're really going to focus on units here in these next few slides. But basically, we're saying f of x is always going to represent some kind of quantity. And if it does, then f's derivative, f prime of x, we could say df over dx, or commonly we use dy over dx right there. But it's going to represent the instantaneous rate of change of that original function. Whether f of x is a particle's position, which we'll get into later tonight, it can basically represent any quantity, such as a circle, outdoor temperature, amount of rainfall, number of people infected with a disease. The true power of the derivative is it gives a way for us to talk about how fast something is changing at a single moment. And instantaneous is really what it's all about, and that's why the calculus is so useful, is we're getting into one particular moment in time, almost like you're watching a video and you're able to hit that pause button at one instant and calculate how fast something's changing right then and there. Now, we've always said, dy dx, and that can be thought of as the change in y divided by the change in x. And basically what that's measuring is the rate at which y is changing with respect, or we could say per unit of x. A lot of times x will be a unit of time, so we could say, gallons per hour, miles per hour, meters per second, those types of things. Just a real quick recap, the x is our independent variable and y will be our dependent variable, and just keeping that little piece of information in mind will pay off down the road. Okay, so let me introduce you to our first example. We've got a function called y of t, and he represents the population. That's our quantity. Our quantity is the number of people of a town over a 20-year period, where y is a differentiable function. Seems irrelevant right now, will play a bigger role down the road. Alright, so here is the populations recorded at selected intervals. So our initial population is 2,500. 4 years later, it had increased to 27,024. 6 years later, we were up to 3,108, etc., etc. So first things first, I want to talk about units tonight. So as I find the derivative, let's say y prime of t is going to be measured in people per year. Okay. Notice the units in the numerator are my dependent variable right here, and the denominator is my independent variable, which would in this case be the t measured in years. Okay, so there's my units. In other words, y prime is measuring the rate at which the number of people in this town is changing per year. Okay, so now what we want to do is we want to find an approximation for y prime of 12. Of course, we'd love to get the instantaneous rate of change at 12, but we don't have enough information in this table. So the next best thing we're going to do, we're thinking if we can't do a tangent line at 12, we're going to do a secant line from 10 to 13 because the 12 roughly falls in the middle of that interval. So I want you to lock in on this interval right here. And what I'm thinking is y of 13 minus y of 10 divided by 13 minus 10. And you know what I'd like to do is I'd like to put y prime of 12 is approximately, I'm going to get my little squiggly sign in there. And we don't want to use an equal sign, we just want to use an approximation sign with a little squiggly brackets there. Equals, of course, y of 13 is going to be that 3,697 number minus 3,108 divided by 3. And now we just got to do a little subtraction and division. Let's see, my subtraction turned out to be 589 divided by 3, which turns out to be about 196.3 repeating. That figures. We didn't get a nice clean number. But let's really work on interpreting and explaining the meaning of this number here in terms of population of the town. So what we're going to say is when t equals 12, in other words, 12 years after we started recording populations, the population of our town is increasing at a rate of 196.3, and I know that's weird to use decimals when we're describing people, but we'll just go with it for now. At a rate of 196.3 people per year. Bingo. And I should probably incorporate the word approximately. At approximately, we'll squeeze that in there somewhere, a rate of 196.3 people per year. Okay, this is kind of a fun one to think about. I'm a big pie fan, and I want you to imagine cooking or baking your pie in an oven that's set at 450 degrees, and when that pie is done, we're going to take it out of the oven, and we're just going to let it sit in a room to cool, and that room is at 72 degrees Fahrenheit. So as you can imagine, as it first comes out, it's very, very hot, it's 450 degrees, and then the temperatures are going to gradually get cooler and cooler and cooler and cooler and cooler, until eventually, if we let it sit long enough, it would reach room temperature. So using the data in the table, we want to find an approximation for y prime of 18. And, like we said, in a perfect world, we find the slope of the tangent line at 18, but we don't have enough information. So the next best thing would be to do a secant line from 15 to 20, just because 18 falls roughly in the middle there. And so let's see if we can go grab this bear. So I'm focusing on this interval right here. And we'll say y prime of 18 is approximately 257 minus 292 all over 20 minus 15. That gives me negative 35 divided by 5, which is equal to negative 7. And we've got to explain the meaning in terms of the temperature of the pie here. And this is the most important part tonight. We'll say at t equals 18, okay? The temperature of the pie, would you say it's increasing or decreasing? Hopefully you are saying decreasing. We're going to say the temperature of the pie is decreasing, and we knew it was decreasing because of that negative sign in front of the 7 at approximately a rate of 7. Now let's grab those units. Let's see if we can pay attention to the units. Now remember, it's always going to be the dependent variables units divided by the independent variable units. Negative 7 degrees Fahrenheit per minute. That's the rate at which it's cooling. Okay, here's a wild one that's worded kind of funny. They define g of x as the amount of time in minutes that it takes to boil a cup of water, assuming it has an initial temperature of x degrees Fahrenheit. And if I just wanted to try to picture this function, and of course I said x was the initial temperature measured in degrees Fahrenheit, and g of x is going to be the amount of time in minutes it takes to boil, I'm going to think that the function looks something like this, perhaps. I'm thinking as the warmer the initial temperature is, the less time it's going to take to boil that cup of water. So anyway, we want to really focus on the units, and I want you to think of it's always going to be the units of the dependent variable divided by the independent variable. So here, our dependent variable, g of x, which you can think of as your y, is measured in minutes. So we're going to do minutes divided by something. And your independent variable is x, and that's measured in degrees Fahrenheit. So I'm going to say the units on g prime are minutes per degree Fahrenheit. Okay, now what's the sign of g prime of 50? And I'm going to give you one approach that you could take here. There are multiple approaches, but I want you to think of this. Remember, and this is kind of why I drew the graph of g earlier, and I made an argument that g is a decreasing function. Remember that g prime measures slope. And what we do know here is the slope of a decreasing function is always going to be negative. So I'm going to say g prime of 50 is negative, and we'll just simply say this. If g is decreasing, that implies that g prime, his derivative, is going to be negative for sure. Here's another interesting one. We said capital T is the temperature in degrees Fahrenheit of a cold yam that was just placed in a hot oven. And T is the number of minutes since the yam was put in the oven. So the first thing is they just want us to work on the practical meaning of this notation right here. And so I'm going to say, well, we say after the yam's been in there for 20 minutes, okay, at T equals 20, the yam's temperature has increased to a temperature of 255 degrees currently. All right, what's the sign of F prime? Well, I'm assuming that as that yam sits in the oven, his temperature is going to dramatically increase. And so we could say if F increases, then the slope of F prime in this case, will definitely be positive for sure. Okay, what are the units on F prime of 20? Okay, think dependent variable, which is the capital T, so that'll be degrees Fahrenheit, divided by independent variable, which is my lowercase t, the minutes. So the units would be degrees Fahrenheit per minute. You'll always find yourself using the word per when describing a derivative, 99% of the time, I'll say. Okay, what's the practical meaning of F prime of 20 equaling 2? We'll say at T equals 20, whoops, forgot my T, at T equals 20, the temperature of the yam is increasing at a rate of 2 degrees Fahrenheit per minute. All right, lock in on that word rate. That's obviously the key word tonight, and make sure you're using that in all your justifications. All right, now we're going to switch gears here quite a bit, and we're going to talk about particle motion. And believe it or not, it is strongly tied in with what we just did, although it may not appear to be on the surface. So hopefully I'll try to tie it all together before we run out of time tonight. But particle motion is basically, we're going to focus on tonight anyway, motion along a straight line. All right, and whoops, having a little trouble spelling here. All right, motion along a straight line. In other words, it's almost like you're running along train tracks and you have the ability to go forward or backwards, but you can't move side to side. Or you can move left to right, but that's it. So and this is a one-dimensional study. And if we were an AB student, we would stop right here after tonight with one-dimensional movements. And then as BC students, we're going to go deeper into this topic once we get to parametrics. And we're going to study this from a two-dimensional analysis. And it's going to really bring it to life, so to speak. But imagine, sometimes you'll start at the origin, but not necessarily. You might start at -2, you might start at 4, wherever you might start. Let's pretend you started at 4, and somebody said, on your mark, get set, go. And you sprinted to the left, and then you turned around, and you sprinted to the right, and then you turned around and sprinted more to the left. And who knows, but that's what we're going to study is motion along a straight line. First, a few basics, okay? We've got x of t, and some books use s of t. I like x of t. This is your position function. In other words, this is going to tell you exactly where you are positioned along the x-axis at a certain time. So if I said x of 2 equals 10, that would tell you that when t equals 2, or 2 seconds after they said go, you're positioned 10 units to the right of the origin. Okay? Now what's interesting about that is you don't actually know what direction you're moving in. You just know your current location is 10 units to the right of the origin. It's possible you could be traveling to the left and be 10 units to the right of the origin. Now, here's the kicker. If we derive that function, okay, we're going to get velocity, all right? Because what's happening here, just like we talked about, and this is where it ties in with the earlier part of the video, let's say the position function is measured in feet per se, okay? And so the derivative x prime would be measured in feet per, we'll say second, some kind of unit of time that corresponds to t. All right. Now velocity is a really powerful function. And here are the basics that we need to know tonight. If the velocity function is positive, that means we are traveling to the right. If velocity is negative, that means we're traveling to the left. Okay, let's focus on that tonight. That'll be one of our big goals. All right. Now let's say we want to take one more derivative just for fun. Let's say we took the second derivative of position, which happens to be the first derivative of velocity. And those that have taken physics could probably make a bold prediction right now and go with the acceleration function, which indeed is what it is. Now, check out these units here. We have, it's going to be the independent variable, or I should say the dependent variable, divided by seconds squared. And you're sitting there wondering, where in the world did you get feet per second squared? Well, here's what happened. We were taking the derivative of velocity to begin with. And so what's happening, you'll notice now velocity was already feet per second. And when we derived it, you'll notice the location of the t being in the denominator. That t right there is measured in seconds. And so when we multiplied the denominators together, you can think of it that way, we got feet per second squared. All right, before we start our first live example, we're going to have a brief discussion about speed. And I want you to understand that it's very closely related to velocity, but it's not the exact same thing. In fact, we're going to define speed as being the absolute value of velocity. We'll see if those physics majors out there agree with that statement. And here's what we need to know tonight. They're going to ask us, when is the speed increasing? Okay, not just positive, but they want to know, when is speed increasing? And here's how we're going to go about it. If, all right, velocity and his derivative, acceleration, have the same signs. Okay? And what I mean by that is they're either both positive at the same time or they're both negative simultaneously, then we'll say the speed is increasing. Now, if that's not true, if they don't have the same signs, then we'll say speed's decreasing. So let's just summarize that here. Speed is going to decrease whenever velocity and acceleration have different signs. One's going to be positive and the other one will be negative. Okay, our first example here, it gives us the graph of a position function. Okay, in other words, the y values just tell me where I'm going to be positioned as I travel along this straight road. And my choices are left or right. That's the only direction I can move in. All right. So we're not starting at the origin. You'll notice my initial position is a 4. So here's my starting location. 1 second later, I'm still standing at 4. In fact, 2 seconds later, I'm still standing at 4. And then what I did is I started to travel leftward. In fact, 3 seconds after they said go, my position is at 0. And that just corresponds to that point right there. 3 seconds after they said go, I'm at 0. 4 seconds after they said go, I'm positioned at -4, okay? And so forth and so forth. We could read the rest of that graph. And I want to talk about, let's answer some questions here. When are we moving to the left? I said basically from t equals 2 until t equals 4. So we'll say from 2 to 4, we're traveling to the left. When are we traveling to the right? Well, after we peaked at -4, we gradually started moving closer and closer to the origin. So I would say from 4 up until 7, we were traveling to the right. When were we standing still? That whole time. We were just locked in at position 4. We weren't moving either left or right. So we'll just say from 0 to 2. I'm not worried about displacement or distance traveled. We'll worry about that when we get into integrals later on. And let's see, what's the particle's velocity at 5? This is a great question. Let's lock in right there. And remember, velocity is going to be the first derivative of position. So we want the first derivative is equivalent to saying slope. So I'm just going to find the slope of that line segment, and I'm going to say something like, let's do -2 minus -4 all over 6 minus 4. And let's say maybe a 2 over a 2, which is a 1, okay? So we'll say the particle's velocity at that moment right there is 1. And we don't really know the units, if it's meters per second or what it might be. They didn't really give us units, but we'll say 1 for right now. All right, now I'm going to throw you a monster curveball now. Just when you probably rewatch that last one a couple of times to digest that graph and so forth. This time I'm giving you a graph of the velocity function, which is a lot different than giving you the graph of the position function. So we're going to work together on this one. And the other trick is, instead of traveling along the x-axis, I want you to visualize this one traveling along a vertical line like the y-axis. So let's picture a big, tall y-axis. Maybe we'll say that's where the origin is. Sometimes we'll be traveling up, sometimes we'll be traveling down, depending on the velocity of the function. Okay, when are we traveling down? Well, like we said earlier, if velocity is negative, we said we were going to travel left. That corresponds to moving down. When is your velocity negative? Starting at 1 and all the way until about, we'll say 2. We'll say 4.2. So from 1 until 4.2, velocity is negative. All right, you can make a little note there in your notebook. Therefore, we're traveling downward. When are we moving up? Well, let's see, from 0 to 1, and also from 4.2 until 6. So 0 to 1, union 4.2 until 6. And the reasoning there would be because the velocity function is greater than 0, it's positive. Okay? Remember that these are all positive values. All the y values on this line segment are a positive, and then same thing over here. All the y values are positive, thus being velocity is positive. All right. When did the particle change directions? All right. What you're going to notice is we change directions at 1 and at 4.2. At t equals 1 and at t equals 4.2. And what you're going to say is we're going to say that v of t changed signs. Okay? In other words, what happened was right there we changed from positive to negative. And then later on we changed from negative to positive. And once we changed signs, that's when the particle turned around and changed directions. Let's see. I'm going to skip these guys right now, and I'm going to pose my own question. When is the speed increasing? Okay, so we're thinking both velocity and acceleration have to have the same signs, and you're thinking, well, I know what velocity is. I've got that picture in front of me, but I don't know anything about acceleration. Oh, but you do, Now remember, acceleration is going to be the slope of this picture, okay? Put that in your notebook. Acceleration equals the slope of velocity. All right. So what I'm going to do is I'm going to make a real quick sign chart. And I'm going to say 3 is when the slope changes signs. Everything from 0 until 3 has a negative slope. So my accelerations are negative. And then everything beyond 3 is a positive slope. Well, and then from 5 to 6, it's just 0. So I better say we're positive, and then we had zeros. All right. Now, right underneath that, we're going to stack a sign chart. So we call this a stacking. And I'm going to make a sign chart for velocity. And it doesn't really matter which one goes on top as long as you make a sign chart for both functions. All right. Now, the velocity function was positive until we hit 1. So I'll put those in there. And then from 1 until 4.2-ish, they were all negative. And then beyond that, they were all positive. So when did we have the same signs? When did we have an overlap of signs? I'm going to say the speed was increasing from 1 to 3 because they were both what? Negative, yeah. And then we'll say from 4.2 until 5, because they were both positive, and as long as both velocity and acceleration had the same signs, we were good to go. So those are the times when speed's increasing. All right, ladies and gentlemen, great job. Way to hang in there tonight. We got a lot to do tomorrow in class. Don't be afraid to ask questions, and we'll definitely need to sort out all the information we've thrown at you tonight. So we'll catch you tomorrow.